right, now we're going to continue on with section 11.1. Just didn't want to do all that in that first video. Gotten kind of long. All right, so now let's look at the idea of what it means to be a matched pair setting. And we're going to flip the page and we'll go back and look at these two type of conditions for a matched pair. And we've talked about matched pair in the past by looking at some experimentation before. So let's look at this example. This happens to be, again, number 13 out of your book. You can actually see where the data is on page 605. So we have the design of controls and instruments affects how easily people can use them. A student project investigated this effect by asking 25 right-handed students to turn a knob with their right hand, and these are all right-handed students, so we don't have that lurking variable in there. And so they turned the knob with their right hands, and that moved an indicator by screw action. So they were turning something. There are two identical instruments, one with a right-hand thread that turns clockwise and the other with a left-hand thread that turns counterclockwise. The table on page 605 gives the times in seconds each person took to move the indicator a fixed distance. So we have, if you'll look at the table, you'll see the situation. And again, these all people were turning with their right hand, and they were either turning the knob in a clockwise direction or they were turning in a counterclockwise direction. And we're trying to see if there's a difference in how they can do these turns. So each of the 25 students used the same instrument. We know if we're going to do some type of experiment, we need randomization. So discuss briefly how you could use randomization in arranging the experiment. So I know somehow I have to have not a specific order in which I have the people do these turning. So I decided to do something like this. I numbered each person 1 to 25 and then pull the numbers out of a hat. And the first 13 would use the turn with their left hand first, and then the other 12 would turn with their right hand first, because I don't want everybody to turn in the same direction. I'd have them all turn with the right hand screwing motion and then having them all turn with the left hand threaded motion. So we want to have that randomly done. So I have to have randomness, remember. I have to have replication, randomness, and if we don't have that, we don't have a legitimate experiment. All right, so now the project hoped to show that right-handed people find right-handed threads easier to turn. So we need to test the data to see if the T procedures are appropriate. So we know we want simple random samples. We're going to hope that that's what happened. And then we need to graph. Now, each person turned with either a right-hand turn or a left-hand turn. So what I need to do is I needed to subtract all of their data, because each person had two measurements, and I want to find out how much faster or slower it took to turn one way versus another. So I had to take all the numbers that were on page 605. I'm going to turn to it real quickly. And in page 605, we knew subject 1, this is how long it took to turn the thread when he turned clockwise, and this is turning counterclockwise. So we can see it took less time for the person to do the thread, turn it to a clockwise motion than in a counterclockwise motion. Person 2 did it exactly the same time. Person 3 was a little bit faster with the right hand, took 3 seconds less, and so on. So I have all these 25 people. So what I had to do is I basically put all of my data in the calculator, and I put all the right-handed threads in list 1, and I put all the left-handed thread times into list 2. And then I had a list 3 in which I subtracted them. Now, which way did I subtract? I let you know that here. I subtracted left minus right. And my method for my madness was I was trying to show that it was going to take longer to turn to the left than to the right. So if I'm predicting that if I take the left-hand turn minus the right-hand turn, that it's going to take longer, and therefore that difference would be a positive difference. So I put all my data, again, for the right-hand turn into list 1, for the left-hand turn into list 2, And then I subtracted them and I got list 3. And I subtracted it list 2 minus list 1. And that was my list 3. And then I graphed only list 3. And I just hit zoom stat to see what type of a histogram I would get. And look, on my graph, it came out to look very, very bell-shaped. Okay, so now I took my list 3 and I found the mean of list 3, which was the mean difference between the times, and I found the standard deviation of each of those. So I had 2 scores from each person, but I had each person, the difference between the 2 times, as a score that I'm really looking at. I'm not looking at the actual amount of time, I'm looking at the difference between the time. Now, I'm going to assume that there is no difference between these two, that the mean should be 0. And I'm going to think that this variability here is just random variability for a distribution, because look how big that standard deviation is. Now, I'm not going to do a two-tail test. I'm going to do a one-tail test because I'm thinking it's going to take longer to turn to the left than to the right. So I'm thinking this difference will probably be something positive. I don't think it's going to be the other way around. The natural motion is, I think, more to turn to the right than to the left for a right-handed person. So we're going to assume that the distribution is centered at 0. However, we got an x-bar up here at 13.32, and we need to find the test statistic and then the corresponding p-value for that. So I did that. Changed it to a t-value. Why? Because this sample standard deviation is something that I don't know what the actual standard deviation is for those differences, so I need to use a t-value. So what I got minus what I'm assuming divided by standard deviation over the square root of n. I have 24 degrees of freedom, calculated my test statistic, which is now a t-value, and then I got the p-value. And once again, let me just quick put my calculator up here and remember the idea of second distribution. Go to my TCDF, you'll never use the PDF, and I type in the 2.90, comma, big number, because I'm finding an upper tail, and then I have to put in the degrees of freedom, which was 24. And so that's about 0.4% or 0.004. Now, I didn't give a significance level. However, regardless of what significance level you use, that's a very, very tiny p-value. So if the mean difference is actually 0, the likelihood of getting this type of value or more extreme barely comes up. So we have evidence against the null. We would say that the mean difference seems to be higher than 0. We can't say it's much higher. All we can say is that it's higher, which means that the right hand does seem to be able to turn faster. The right hand in a right hand thread seems to turn faster than having a left hand thread. Now the last thing we're going to look at is a type 2 error and power. And going back to the previous example that we just looked at, I want to find what's the likelihood, or how much power do I have if I use this sample size of 25 to test against the alternative that the mean difference is 10 seconds. So I'm going to assume it's this, and I want to find what is the likelihood that I'm going to be able to, I want to find power, so reject the null when the null in fact is wrong and the mean difference in the time is actually 10 seconds. And I'm going to use an alpha level of 5%. So what do? Same idea as what we did before, except we're going to be using a little different t-value rather than a z-value. So we know that a power is the likelihood of rejecting the null when an alternative is true. So we can either find the rejection zone or the acceptance zone. And I've set up my picture here to find the acceptance zone. Remember, rejection zone would be down here. So our picture is centered at 0 to begin with, and I'm using a 5% significance level, so I need to find this value that has 5% down here. 0.05 would be the area down here. And once again, if I take my table, and I know I have 24 degrees of freedom, 24 degrees of freedom, and I want the upper tail to be 5%. So I would come down here and look for that T star value. So that T star value that has 5% in the upper tail is positive 0.1711. I can see it's positive, just like a Z value would be positive if we had known the standard deviation of the population. And so I need to find this number. So what do? I know that I'm 1.711 standard deviations higher than the mean, so I can either go to this. I can also write it like this, that the t value is what I got minus what I'm assuming divided by the standard deviation over the square root of n. This is the 1.711. I don't know that. I know I'm assuming that is 0. And from a previous sample, so I would have to do some sampling to get an idea of what this was going to be for the standard deviation, and then go through and do the algebra to find that x bar. So I'm getting this x bar value to be 7.849. And then I know that the acceptance zone is when I have x bars that are less than or equal to that value. The rejection zone if I were greater than that value of that x bar. And so I'm finding the type 2 error, and then I'll find the power afterwards. So the type 2 error is what's the likelihood of the acceptance zone if the alternative mean difference is actually 10 seconds. So my new picture with 10 here in the center. And my acceptance zone was 7.849 and lower, which is approximately here. And so I found that by converting it to a t value. Again, it's just a t value rather than a z value because I don't know this standard deviation. And then I use normal CD or TCDF in order to calculate this, again with 24 degrees of freedom. So the likelihood that I will accept the null when the null is actually false and the mean difference is really 10 seconds, that's going to happen about 32% of the time, which means my power is 0.68. 68% of the time I will reject the null when the null is actually wrong and the difference in times is actually 10 seconds. So you can see it's much the same as what we did as far as testing before. The only difference is we don't know the population standard deviation, therefore we have to use a t statistic rather than a z statistic. And you'll also see that your book actually has some values on these t values for degrees of freedom that go up to sample sizes by ones up to be a sample size of 31, and then it starts doing some jumping. Some textbooks, once you get past 30, will automatically use a z value, but we might as well use these since these are available to us. Now, a couple other things. I didn't mention one term up here that we will need to be responsible for knowing. We are responsible for knowing, and is the term robustness. And the robustness is the idea, basically it's, can I use this test if some of my assumptions are not holding? And you want simple random samples. So except in small sample sizes, the assumption that our data is from a simple random sample is more important than the assumption that the population is normal. You really need unbiased data, and that's going to come from having simple random samples. Now, if you have simple random samples, remember we really want our population to be normal. What happens if it's not normal? If our sample size is quite small, less than 15, and you can see that you have some, if the data is close to normal, you're good to go. However, if you see some really abnormal graph or some outliers in there, then really the statistics that we calculate and the decisions we make are not going to be very valid decisions. So graph the data, look at it. If it looks pretty normal, then you are still good to go. On the other hand, what if your sample size is roughly 15 or higher? If you don't see strong outliers and strong skewness, then you really can use these t values for confidence intervals and for hypothesis testing and be quite confident that the values you get are going to be pretty representative of your population. So as long as you keep the population, if you keep simple random samples, then we can work with actually quite small sample sizes and get some good information. If you'll remember, we were working with some sample sizes of only 6 previously. Now, we were told that they were normal populations, but simple random samples, very, very important. Graph the data. If it looks approximately normal, at least if you don't see some outliers, you're usually good to go, which means this test is quite robust. Something that's not robust would mean, whoa, if it doesn't look normal as a graph, then don't do the test because it's going to really mess up on confidence intervals and hypothesis tests. So if it's robust, that means that your results for your p-values and your confidence intervals are not going to vary by much on this test if you don't have, exactly normal data. All right, now we're done with section 1.